Hello. In this video we will solve question number 13 from GATE 2020 chemistry paper. Now the question is the following. Among the following linear combination of atomic orbitals, which is the correct representation of the lowest unoccupied molecular orbital of butadiene molecule? Now these are the four options that are given. Now first let's understand some of the background. Now this is the structure of butadiene. It has 4 carbon atoms. Each carbon atom is sp2 hybridized. Now let's say the molecule is on the xy plane. So each carbon atom has an extra pz orbital. So the butadiene molecule has 4 different pz orbitals, and these 4 pz orbitals will overlap with each other and will form 2 pi bonds. So the butadiene molecule has overall 4 pi electrons. Now the next question is, how do we construct molecular orbitals starting from different atomic orbitals? The orbital is basically a 1 electron wave function. So we can construct different molecular orbitals by linearly combined different atomic orbitals with proper or appropriate coefficients. This method of constructing molecular orbitals is popularly known as linear combination of atomic orbitals, and in short LCAO method. Now let's say the capital psi is a molecular orbital wave function, and phi 1, phi 2, phi 3 and phi 4 are 4 different atomic orbital wave functions. Now for the butadiene case, phi 1, phi 2, phi 3, phi 4 are 4 pz orbitals. Now mathematically we can write down the molecular orbital wave function psi equal to c1 phi 1 plus c2 phi 2 plus c3 phi 3 plus c4 phi 4 with coefficients c1, c2, c3 and c4. Now these coefficients must satisfy the following criteria, which is the sum of I equal to 1 to number of participating atomic orbital wave function. That means for the butadiene case it is 4. So sum of I equal to 1 to 4, mod of Ci square equal to 1. Now the number of molecular orbitals will be equal to number of participating atomic orbitals. So for the butadiene molecule, 4 different atomic orbitals will overlap and will form 4 different molecular orbitals. Now let's understand the concept of node. At the position of nodes, the wave function changes its sign. That means the phase of the wave function will change at the position of nodes. And at the position of nodes, the molecular orbital wave function, that means psi equal to 0. That means the probability density mod of psi square will be also equal to 0. So the probability of finding the electron at the position of node will be equal to 0. Now the lowest energy molecular orbital has 0 node. The next molecular orbital has 1 node. The next molecular orbital will have 2 nodes, and then 3 nodes, 4 nodes and so on. Now the energy of the molecular orbital increases with the increase of the number of nodes. Now electrons will fill up from the lowest energy molecular orbital to the highest energy molecular orbital, and HOMO is the short form of the highest occupied molecular orbital, and LUMO is the short form of lowest unoccupied molecular orbital. Now let's look at the pi molecular orbital diagram of butadiene molecule. So butadiene molecule has 4 different pz orbital. Now this dark region means this lobe is positive phase, and the white region means this lobe is in the negative phase. So these four atomic orbitals of the butadiene molecule, which is the four different pz orbitals, will overlap with each other and will form four different molecular orbitals. Two will be the bonding molecular orbital and two anti-bonding molecular orbital. Now the lowest energy molecular orbital, let's call it pi 1 molecular orbital, has 0 node. That means all four pz orbital will overlap with each other in the same phase. So these four pz orbital, that means, are overlapping with each other in the same phase. Now next molecular orbital, let's call it pi 2 molecular orbital, has one node. That means the phase of the pi 2 molecular orbital wave function will change once. So here these two lobe has the is in the positive phase and these two lobe is in the negative phase. So that means the phase of the wave function is changing here at this position. So pi 2 orbital has one node and these are the nodal plane. The next molecular orbital, let's call it pi 3 star. Star means it is the antibonding molecular orbital. So pi 3 star molecular orbital will have two nodes. That means the phase of the wave function will change two times. So here this lobe is in the positive phase, this lobe is in the negative phase. That means here the phase is changing. Then the third lobe is in the negative phase. That means here the phase of the wave function is not changing. Then here the fourth lobe is in the positive phase. So here the phase of the wave function is also changing. That means the phi 3 star molecular orbital will have two nodes at this position and at this position. The next pi 4 star molecular orbital will have three nodes. That means the wave function will change its sign three times at this position, and this position. Now let's fill up the electrons. So the butadiene molecule has 4 pi electrons. So the 2 electrons will be placed in pi 1 molecular orbital and the other 2 electrons will be placed in pi 2 molecular orbital. So for the butadiene case, which will be the lowest unoccupied molecular orbital? This pi 3 star. And the lowest unoccupied molecular orbital, that means LUMO, will have two nodes. That means the phase of the LUMO wave function will change two times. Now let's see some useful tricks to solve this kind of problems. So first, draw the structure of the molecule, then count the number of pi bonds or the number of pi electrons, then draw the molecular orbital diagram for the pi bonds, then fill up the electrons from the lowest energy molecular orbital to highest energy molecular orbital. Then identify which is the highest occupied molecular orbital, that means HOMO, or which is the lowest unoccupied molecular orbital, that means LUMO. Then count the number of nodes the HOMO or LUMO should have. Now, at the previous slide, as we saw that at the position of node, the phase of the wave function or the sign of the wave function will change. So just look at the various options that are given and just pay attention to the sign of various coefficients. Now, by just looking at the sign changes of the different coefficients, we can count the number of nodes in that particular state. Now, the last is identify the correct option with the correct number of nodes. Now, let's solve for the butadiene case here. Now, let's look at the option A. Here capital psi is the molecular orbital wave function. Phi 1, phi 2, phi 3, phi 4 are 4 different atomic orbital wave functions, and these are the coefficients. So here C1 has negative sign. So C1, phi 1 is contributing with a negative phase. That means the dark region will be here. Then the phi 2 is contributing with a positive phase. That means this. Then C3 has negative sign, so phi 3 is also contributing with a negative sign. Means here. And C4 has positive sign, that means phi 4 atomic orbital is contributing to the molecular orbital with a positive phase. That means this. So here the phase of the wave function is changing 3 times, like here at this position, at this position, and at this position. Now we need to connect negative to negative or positive to positive. So if we connect here, so we can clearly see the phase of the wave function is changing here at this position and at this position. Now let's look at the option C. Here C1 has the positive sign, so phi 1 atomic orbital is contributing with a positive phase. C2 has also positive sign, so phi 2 atomic orbital is also contributing with a positive phase. Then C3 has negative sign, so phi 3 atomic orbital is contributing with a negative phase. And C4 has the negative sign, that means the phi 4 atomic orbital is contributing to the molecular orbital with a negative phase. Now if we connect positive to positive or negative to negative, we can clearly see the phase of the wave function changes here. So the phase of the wave function is phase of the wave function changes once. So this particular molecular orbital wave function has one node. It has 3 nodes. Now let's look at the option D. So C1 has the positive sign, that means the phi 1 atomic orbital is contributing with a positive phase. C2 has the positive sign, that means the phi 2 atomic orbital is also contributing with a positive phase. Phi 3 atomic orbital is also contributing with a positive phase, and phi 4 is also contributing with a positive phase. That means the phase of the molecular orbital never changes. That means all 4 different atomic orbitals are contributing to the molecular orbital in the same phase. That means this particular molecular orbital has 0 node. Now let's look at the option B. Here C1 has the positive sign, that means the phi 1 atomic orbital is contributing with a positive phase. Then C2 has the negative sign, that means the phi 2 atomic orbital is contributing with a negative phase. Then C3 has the negative sign, that means the phi 3 atomic orbital is contributing with a negative phase. And C4 has the positive sign, that means the phi 4 atomic orbital is contributing to the molecular orbital with a positive phase. So if we connect now positive to positive or negative to negative lobe, we can clearly see that where the phase of the wave function is changing. Now if we connect here, we can clearly see that at this position the phase of the wave function changes, and at this position the phase of the wave function changes. So the option B, that is the molecular orbit, this particular molecular orbital wave function will have 2 nodes. Now, as we have seen from the previous slides that for the butadiene molecule, the lowest unoccupied molecular orbital, that means LUMO, has 2 nodes. So the option B have also 2 nodes. So that means the correct option is the option B. Now for further details, you can visit the following NPTEL references, and the respective YouTube links are given here.